Lockheed P-38 had the extra space needed to house the turbocharger. It was a big twin-engined aircraft to begin with, and had space in its tail booms for the extra equipment. But given the size of the P-38, it wouldn't have fared well against nimble single-engine German fighters in a dogfight. America had other smaller fighters powered by the Allison engine, the P-39 Airacobra and the Curtiss P-40 Warhawk. In both cases, their manufacturers failed to include Allison's turbocharger. The P-39 had an innovative layout, with its engine situated mid-fuselage, behind the pilot. It was designed to house both the Allison engine and the turbocharger. However, a scoop built into the left side of the fuselage to cool the turbocharger was deemed too aerodynamically expensive. Both the scoop and the turbocharger were eliminated from the production design. This change crippled the Aerocobra's ability to fight at high altitudes. In the case of the P-40 Warhawk, a rugged, single-engined airplane, the turbocharger was excluded from the design from the get-go. This limited its optimal altitude to just 15,000 feet, and thus relegated the aircraft to ground attack work. The British Purchasing Commission was still interested in the Warhawk, even with its limitations. They saw it as more of an Army support aircraft. However, the Curtiss factory was running at capacity and could not fulfill the order. With no suitable aircraft readily available for purchase, the Brits would turn to North American aircraft. The British Purchasing Commission proposed that North American build the Warhawk under license from Curtiss. But NAA President Dutch Kindleberger had a bolder plan. He guaranteed that he could create an even better airplane, using the same Allison engine, in less time than it would take for him to retool for Warhawk production. The Brits said yes, and the end result was an airplane that may well have changed the outcome of the Second World War in Europe. Back in Europe, Germany was looking for an aircraft to augment the Bf-109. In the Battle of Britain, the Bf-109 and Spitfire were closely matched. But the Bf-109 lacked the range to be highly effective in its escort role over Britain in the summer of 1940. The Luftwaffe had a twin-engined escort, the Bf-110. It had the range to be an excellent escort, but it lacked the maneuverability to defend itself or its charge in a dogfight. It also used two Daimler-Benz 605 engines, making it an expensive sitting duck for British interceptors. Looking for a quick solution to their escort dilemma, the Luftwaffe even considered having the 110s tow 109s into battle to conserve fuel. But in the long run, using two aircraft to perform the role of a single fighter was an even more wasteful solution. What the Luftwaffe needed was a dedicated single-engine aircraft to fill in for the Bf-109 on longer-range missions. And ideally, something to give them a decided advantage over the British fighters of the time. However, the Luftwaffe wanted to have its cake and eat it too. They wanted a new fighter, but they didn't want to sacrifice any of the precious 605 engines meant for the Bf-109. To the consternation of the Luftwaffe, most of the new submissions for fighter designs from German industry were to be built around this very same engine. To solve Germany's escort woes, one man, Kurt Tank, Focke-Wulf's legendary designer and test pilot, did what was almost unthinkable at the time. Since the start of the war, British and German designers had relied upon powerful 12-cylinder inline engines to power their fighters. Tank dared to build Germany's next fighter around a bomber's radial engine. The air-cooled BMW 801 radial engine had plenty of power and had proven reliable in the Ju-88 and Do-217. But radials in a fighter were a rare sight in Europe. It was difficult to build as aerodynamic a fuselage to house them in as when constructing one for a slender inline engine. Though an unconventional design track, Tank saw two reasons for encouragement. Firstly, The National Advisory Committee for Aeronautics in the U.S. had already done research on improving airflow around radial engines. Over time, they had developed the NACA cowl, which at least helped to reduce drag. This was a simple ring which fitted snugly around the cylinders of a radial engine. It not only made the engine more aerodynamic, it also improved cooling. Secondly, Tank observed that the U.S. and Japanese navies were employing several modern carrier aircraft, all with radial engines. Aircraft like the F-4F Hellcat and the Japanese A-6M-0. The lightweight Zero had been almost unstoppable in the early part of the Pacific War. Tank had continued to explore ways of improving his new radial-engined aircraft and reducing the drag effect, although some say his greatest task was selling the radial idea to the ministry. If that was the case, the bureaucrats must have been quickly won over by Kurt Tank's first prototypes. Given the designation the Focke-Wulf 190, and unofficially known as the Butcher Bird, the Luftwaffe's latest fighter was rushed into production. Fortunately for the Allies, the FW-190 arrived after the close of the Battle of Britain. In the summer of 1941, 5 Mark V Spitfires flying over the south coast spotted several radial engine fighters in German markings. At first glance, they were mistaken for U.S.-built Republic Lancers. It was a deadly case of mistaken identity. The aircraft were, in reality, early model FW-190s. The Spitfire pilots who survived the ensuing battle lived to tell just how quickly their comrades had been lost. But Britain's greatest loss that day was not pilots or planes. The battle marked the day Britain lost air superiority to the Luftwaffe. The RAF had to do something, and fast. All eyes looked to Rolls-Royce, manufacturer of the Merlin engine, the power plant of the Spitfire, Hurricane, and so many of Britain's great planes. Although the company had the next-generation engine, the 12-cylinder Griffin in development, it was well over a year away, more than enough time for Britain to lose the war. Earlier, there had been some thought given to modifying a few Merlin engines for experimental high-altitude work to be executed by a Wellington bomber. It was little more than an idea at the time, but in Britain's hour of desperate need, Rolls-Royce engineers worked night and day to test the concept. Merlin engines were already supercharged. An air compressor mechanically attached to the rotating camshaft increased the airflow to the engine, allowing it to burn more fuel and to boost performance. Rolls-Royce engineers had theorized that adding a second supercharger could give the engine even more punch during high-altitude work. Might a two-stage supercharger help the RAF reclaim air supremacy? The end result of the Rolls-Royce experiments was breathtaking. It was almost as if the two-stage, two-speed Merlin was an entirely different engine, when in fact it was just a modification. When the double supercharged aircraft, dubbed the Spitfire Mark IX, finally arrived in June of 1942, the RAF had a rare opportunity to test it directly against the captured FW-190. The test results were far different than the day a group of unlucky RAF pilots ran into a flock of butcher birds. The two aircraft were virtually equals in terms of performance. Captain Eric Brown, who had flown a captured FW-190, had a chance to test the new Spitfire 9 against the German aircraft in live combat.
I'd flown the 190 quite a bit, so I wasn't too frightened. I reckoned I knew what that aircraft could do, and I knew what my Spit could do, so I thought, well, I can handle this guy. Hoping he was somebody just out of training school. But no, I picked somebody who really knew what he was up to. And we had, I would say, a to-ing and fro-ing over France. But neither could get a draw beat on the other. We finally realized, as both of us, we run out of fuel. We waggled our wings at each other and departed. And I realized this was really a top not fighter aircraft.
The RAF had leveled the playing field with the Luftwaffe, at least for the time being. But what the RAF really needed was an aircraft to give them the upper hand. The new Merlin's greatest contribution to the war was still to come, when it was mated with an extraordinary aircraft of American design. Back in the U.S., North American Aircraft had continued to work on a Warhawk substitute, which met the specifications laid out by the British Purchasing Commission. They had specified that the airplane be powered by an Allison engine, that it cost less than $40,000, and that it be armed with 4.303-inch machine guns. North American answered with the P-51 Mustang. It featured an advanced laminar flow wing for good aerodynamic efficiency and a wide gate undercarriage for safer landing. Pleasing to the eye and to fly, although mainly at lower altitudes, the new arrival quickly gained respect from pilots and ground crews alike. There were some concerns about how the Mustang would fare should it be forced to ditch while crossing the channel. During a water landing, its air scoop, located beneath the fuselage, might flood the aircraft or cause it to overturn. Water tank tests at Saunders Row were initiated to perfect the techniques for ditching the aircraft. Around the same time that the RAF was getting the Spitfire Mark 9 ready for combat, and the FW-190 was dominating the skies, Rolls-Royce test pilot Ronald Hawker was tasked with the mission of evaluating all aircraft powered by non-Rolls-Royce engines. He was thoroughly impressed with the P-51A, save for its poor performance at high altitude. Like the P-40 Warhawk, it had an Allison engine and no turbocharger. Hawker pondered how the aircraft might perform with the new Merlin engine. The results on paper were phenomenal. According to Rolls-Royce's calculations, with a Merlin power plant, the Mustang would not only outclass any American aircraft, but even new Spitfires using the same engine. Oddly, Hawker had to push for the mating of the Merlin 61 and the Mustang, even though the double supercharged P-51 would have outclassed the FW-190 as well. Hawker finally arranged for the marriage of the two great inventions, and test trials confirmed his hunch. The Mustang was a war winner. The main challenge was to produce enough aircraft and engines to reclaim the skies of Europe. North American would tweak the Mustang design to accommodate the Merlin 61 engine. It was a much more powerful engine, so the original P-51A airframe had to be reinforced. As well, the three-bladed prop was exchanged for one with four blades. The addition of plumbing for drop tanks might have seemed a small change, but it would have a great impact on the air battles to come. Packard took up manufacture of the Merlin 61 engines in the U.S. They were designated the V-1650s. Packard had arranged a licensing agreement with Rolls-Royce earlier in the war. Ford was originally slated to build American-made Merlins and seemed a perfect choice due to the company's industrial might. But Henry Ford was adamant that his company build defensive weapons only. North American's double supercharged aircraft, the P-51B and P-51C, first took flight in the spring and summer of 1943. Air Vice Marshal Paddy Harbison recalls when the Mustangs first arrived at his Spitfire squadron.
Of course, the Mustang was a revelation. It was a much more comfortable airplane than the Spitfire was. And I have heard people talk about the relative merits of both. They were both war winners. The Spitfire was built as an interceptor. It could outturn a Mustang and it could outclimb it, but it didn't have the legs the Mustang had. And of course, if you can't get to where the fight is, you're not too effective.
As P-51 started to arrive in Europe, the war was changing, and the Mustang was the perfect aircraft for the time. The U.S. was taking the war to Germany. They were bombing the German war industry out of business. The only problem was their bombers were being shredded by speedy German interceptors. The U.S. had hinged their hopes on the ability of their bombers to defend themselves by maintaining a tight box formation. When this strategy failed, they were in dire need of an escort fighter. The P-38 Lightning was simply not agile enough to take on the role. Then there was the P-47 Thunderbolt. It was an awesome radial engine fighter, more than capable of taking care of itself in battle. But it had two major flaws. It was expensive, and it lacked the range to take the bombers all the way to Berlin and back. The P-51Bs and Cs arrived just in time. They had been designed to carry drop tanks, and with the addition of a fuel tank behind the pilots, they had more than enough fuel to escort American bombers to Hitler's lair. The Mustang proved more than a match for Germany's FW-190 and ME-109. Slowly, American bombers closed in around Berlin. Suddenly, the Germans found themselves playing catch-up. Kurt Kampf's FW-190 with a radial engine found it difficult at higher altitudes where the bombers roamed. Kampf swapped its radial engine for an inline. The long-nosed aircraft was nicknamed the Dora.
The Focke-Wulf Dora, the later Dora, was a magnificent fighter with an engine change. Not really any structural changes other than those to accommodate the engine. But what it meant was, here was an airplane that could keep up with the hunt as the years of the war progressed. So from 1942 right up to the end of the war, the Focke-Wulf 190 was in the top grade of fighter or fighter bomber.
The P-51 Mustang also continued to evolve as mechanics and engineers incorporated changes based on the feedback of pilots who had tested the plane in battle. Its canopy went through several permutations. The British swapped the original one for a sliding Malcolm hood, similar to a Spitfire's for improved visibility. The P-51B, the definitive version of the Mustang, had a bubble canopy, which offered 360 degrees of clear view. North American also upgraded the D's firepower. It had 650 caliber machine guns compared to 4 in earlier models, and it had solved the problem of gun jamming during hard turns. The fuel tank situated behind the pilot may have increased range, but it created other issues. The plane had poor directional stability when the tank was full. To counter this problem, engineers added a small dorsal fin in the D model. These and other improvements would help the Mustang blaze a path to Berlin for America's bombers. Reichsmarshal Hermann Göring, commander of the Luftwaffe, was quoted as saying, "When I saw Mustangs over Berlin, I knew the jig was up." When the European war had come to a close, the battle still raged in the Pacific. The Mustang was the best escort available, but even with its incredible range, it could not accompany an aircraft like the B-29 Superfortress on extended bombing missions over Japan. The expanses of ocean were too large. The engineers at North American struggled with the problem of stretching the Mustang's range. Their solution was a Zwilling or twin Mustang. By fusing two Mustangs together, they hoped to dramatically increase the range of the Mustang while retaining its excellent dogfighting abilities. The new Mustang, the F-82, had an incredible range, 2,000 miles. Though the prototypes were powered by Packard-built Merlin engines, the U.S. Army Air Corps was adamant that the production version be totally American-made. Unfortunately for the F-82, without Merlin engines, it was not the same aircraft. When fitted with the Allison V-17-10-100, its speed dropped and high-altitude performance suffered. It was one of the few cases of a prototype outperforming the production model of an aircraft. By the time the F-82 was ready, Japan had surrendered and the war was over. After the war, the P-51 continued to serve, while other piston engine fighters of the era went quietly into retirement. Though it was the dawn of the jet age, there was still a place for the Mustang in a variety of roles. Colonel Ray O. Roberts flew the Mustang during its second life.
At that time I was flying what they call the F-6, which is a P-51 with cameras. Also had guns, and you could have the bombing and gunnery capability. And we participated in a post-hostilities mapping program. We revised all the Japanese maps, photographed, did aerial photography in Japan and Korea.
When the Korean War arrived, Mustangs which had been mothballed for long-term storage were suddenly being shipped across the Pacific on carriers. Unable to compete with the next generation of jet fighters for the dogfighter role, Mustangs returned to where they started. In Korea, Mustangs made excellent ground attack aircraft.
Trade in for Pixel 8a. Get the phone with Google AI for less with an eligible trade-in.
They didn't have the speed of jets, but they had the endurance to make it from Japan to Korea on bombing runs. In Korea, the F-82 also had an opportunity to taste combat for the first time. F-82s flew strike, escort, and night fighter missions. The marriage of the P-51 Mustang and the Merlin 61 engine produced incredible results. It provided the Allies with an effective escort to pound the last nails into Germany's coffin. Perhaps the most amazing thing about the P-51's stellar career is that it might never have happened. If the Merlin and Mustang had never been mated at the suggestion of Hawker at Rolls-Royce, the P-51 might have had a humdrum career as a reliable ground attack aircraft, rather than an elite dogfighter. It arrived at the right time and the right place in history, just when the Allies needed an escort fighter. The P-51 was the end result of years of aircraft and engine development. Though jet-powered aircraft would supplant it, the impact of the Mustang and Merlin in military history cannot be unwritten or denied. At the Farnborough Air Show in 1949, barely 4 years after the war ended, Britain presented an impressive array of jet aircraft. Some were purely military, others experimental, and there were even some airliners converted from piston engines to the new jet technology. Perhaps the best crowd pleaser was the advanced de Havilland Comet turbojet airliner. Elsewhere in England, other types of jet airliners were being developed, but these were somewhat different. This is the Vickers Viscount airliner. When it first came into service in the early 50s, it quickly became a success. One of the main reasons for the Viscount's ever-expanding order book was the aircraft's Rolls-Royce Dart turboprop engines. However, the Viscount wasn't the only contender, nor was the Dart the only turboprop engine available at the time. Slightly smaller than the Viscount and with different turboprop engines, the Armstrong-Whitworth AW-55 Apollo was no less pleasing to the eye, and in tandem with the Vickers aircraft, represented a giant step forward in airline design. The target market for both aircraft was the short to medium routes of the emerging post-war airline industry. With government backing British industry, they had something special to offer with the revolutionary turboprop engines. The concept of a conventional jet having its exhaust thrust converted into turning power for traditional propeller blades was brand new, and it made for extremely economical and very smooth running. There were two early examples, the Rolls-Royce Dart and the competitive Armstrong-Siddeley Mamba. The Apollo's designers favored the Mamba, whereas Vickers chose the Dart. Construction of the Apollo started in Armstrong-Whitworth's factory at Baggington Airport in 1948. Baggington had been bombed during the German Blitz on Coventry. It was used as an RAF fighter base during the war years, but now it would be used as part of Britain's critical export drive to repay the war debt. The there were grounds for optimism as the country refocused its industry. Only 3 years earlier, manufacturers had produced Spitfires and Lancasters by the thousands, and for a time, most of the skilled aircraft builders were still on hand. One of the more notable features of the Apollo's Mamba engines was their narrow diameter. Slender and aerodynamic, they complemented the aircraft's aesthetics. However, the smaller engine housings that accompanied the Mamba did not provide for an area to store the landing gear in flight. This meant that the main wheels had to retract into the fuselage, consuming valuable space. However, the Mamba still showed great promise. Apart from anything else, it had already powered a trainer, the Athena, which was actually the first production aircraft to employ a turboprop engine. Also, early tests suggested good performance. In 1948, a 500-hour test run confirmed the engine's durability. After this, Armstrong and Whitworth were sure that they had a winning combination. The AW-55 Apollo prototype was designed and built to accommodate a crew of 3, 2 pilots and 1 cabin crew. Passenger seating could be configured for up to 31 people. However, a slightly longer version for production had also been discussed, as well as a military version for troop transport. Construction on the Apollo progressed until its rollout in April of 1949. This sleek, fully pressurized airliner was a far cry from the utility fighters and bombers the industry had produced just a few years before. On the 10th of April, Apollo aircraft serial number BX-220 took to the air from a grass field at Baggington Airport. Its first flight lasted just half an hour, and the results were less than impressive. The first problem was that the Mamba ASM-2 engines failed to produce the 1,200-plus horsepower expected, which were indeed needed to meet the aircraft's performance requirements. The 800 horsepower that was actually recorded was far short of what was anticipated. Subsequent test flights also demonstrated numerous flaws in the airframe design. Improvements were constantly made until a critical flight test to Paris and back was undertaken on the 12th of March, 1951. Still, problems persisted, with the Apollo having a flawed airframe and the Mamba engines remaining underpowered. In June of 1952, all further development on the Apollo was abandoned, and the only 2 examples ever built were used for research work at Boscombe Down. This left the Vickers Viscount the undoubted winner, and it was this type that also went on to become one of Britain's all-time airliner export earners, with 445 built. The redoubtable Rolls-Royce Dart turboprop engine was even more successful, with over 7,000 engines delivered to numerous customers up until 1987, 41 years after its first test. For a while, the Armstrong-Siddeley Mamba had no such success, but then again it certainly wasn't a complete failure either. Rather, with improvement, it morphed into several different life forms, each one displaying considerable and unexpected ingenuity. At about the same time that the Apollo was under construction, the Royal Navy and Fairey Aviation were developing a truly remarkable anti-submarine aircraft. The Fairey Gannet shared the same problems as many carrier-borne aircraft. It had the performance needs of 2 power plants, but this usually meant the high risk of possibly having to land with one engine not functioning. This type of asymmetric approach is highly dangerous for the aircrew. A second consideration for Fairey's designers was the significant economy that might be achieved on long missions if one of 2 engines could actually be turned off, and yet still leave the plane with the same balance as a single-engined aircraft. Armstrong-Siddeley thought that they might have the answer. The very narrow diameter of the Mamba turboprop might now prove most useful if 2 could be assembled side by side, driving 2 contra-rotating propellers, both able to be turned on and off independent of the other. The Double Mamba, as it became known, was a major success. providing Gannett pilots with 2 jet power plants in an aircraft that had great range and at the same time was safe to land even with one engine down. Because of its Mamba engines, the Gannett became a much trusted maritime aircraft, which went on to serve in a number of other countries. With nearly 350 of all types made, it wasn't so far off the numbers of Viscounts delivered, although the Vickers plane had 4 turboprops as opposed to the Gannett's 2. Still, the versatile Mamba had much more to offer. By removing the gearbox and the propeller drive, Armstrong Siddeley were able to present a conventional turbojet. With a few more deletions and economies, this evolved into a so-called expendable power plant, and it transpired that there actually was quite a market for a short-life jet engine. It was named the Adder. Post-war Western governments knew that they might have to deal with Soviet forces that would include jet aircraft. Target practice on anything flying less than in the high 500 miles an hour range would be useless. Equally important, a target would have to be able to fly up to a height of 50,000 feet and get there quickly, since most drones only have a limited flight time.
Who you got to work with when your eyes are closed in the forest? Who you got?
In 1948, the Australian Government Aircraft Factory entered into a contract to develop an unmanned radio-controlled flying target. It was given the name Jindavik, Aboriginal for the hunted one. Made in Australia, many were shipped to Britain in parts, where, with their experience with the Mamba engine, Fairey Aviation assembled each unit that was powered by the Mamba's descendant, the Adder. More than 500 Jindaviks were built and employed by Australia, Britain, the United States, and Sweden. Over time, Armstrong Siddeley merged with their rivals, Rolls-Royce, although not before it had redeveloped the Adder into a stronger and more reliable turbojet. The end result was also much more powerful. It was named the Viper, and Vipers were produced in the hundreds, powering the Jet Provost, Strike Masters, Hawker Siddeley 125, and many more. What started out as a misfire with the Mamba engines on the Apollo developed over time into a successful line of engines with the double Mamba, Adder, and Vipers that would power numerous aircraft for years to come.
One problem facing the designers of the next generation of turbojet engines is that of increasing turbine inlet temperatures. Air-cooled turbine blades may offer a solution to this problem. The fabrication of a cast air-cooled turbine blade that has shown promise in prototype testing will be shown in this film. This blade was made using a modification of the lost wax casting technique. A process to provide long, slender holes for cooling passages was developed by the Lewis Flight Propulsion Laboratory of the National Advisory Committee for Aeronautics. This development is particularly important because the super alloys used in aircraft turbine blades are extremely difficult to machine. Ceramic tubes are used as part of the casting mold to establish cores or holes through the turbine blade casting. Core tubes of the desired outside diameter are assembled in a patterned die. The core tubes are held in place by embedding them in a bar of soft wax using a hot wire or knife. The dies used are made of a low-melting alloy cast around a brass master pattern. A casting pattern is made by closing the dies containing the ceramic tubes, clamping the dies in a wax injection machine, and injecting molten wax under pressure. The wax pattern containing ceramic tubes is removed from the die, and excess wax is trimmed, leaving a light wax film on the exposed ceramic tubes to permit freedom of movement due to expansion. Additional pieces of wax are assembled by welding with a hot wire. These pieces will form sprues, runners, and ingates or passages for the molten metal to reach the blade cavity in the casting mold. The assembled wax is mounted on a waxed base to seal it. A can-type flask is placed over the assembly, and it too is sealed at the bottom. When the investment is thoroughly mixed, it is poured into the flask and around the wax pattern assembly. The flask is then placed in a vacuum chamber to remove air from the mix. After investing and air drying, the molds are placed in a furnace. Here the drying is completed, the wax is melted out, the wax residue is burned off, and the mold is cured. During this furnace cycle, the temperature is gradually increased from room temperature to 1900 degrees Fahrenheit. Metal alloy for the casting is melted in an electric induction furnace. When the metal reaches a temperature of 3000 degrees Fahrenheit, the crucible of molten metal is placed in a centrifugal casting machine, and the hot mold is placed over it. As the casting machine is spun, the molten metal is thrown into the mold. The casting is removed by breaking away the mold. After the casting is cleaned up, the ceramic tubes used to form the cooling passages in the blade must be removed. This is done by threading fine stainless steel wires through each ceramic tube and stretching them taut on a frame. The turbine blade is then attached to a cam device designed to slide the blade up and down on the wires. The lower part of the assembly is then immersed in a bath of molten caustic. This helps to remove reaction products and introduces fresh caustic to the bore of the tubes, and hence accelerates the solution and removal of the core tubes. The rough casting is cleaned in an air-water abrasive blast. A suitable base configuration is then ground, and the blade is ready for testing in a research facility. The process you have just seen illustrates a principle that has been effective in producing long, thin-cored holes in castings. This process may be useful in fabricating turbine blades to be used at very high turbine inlet temperatures.
Most men don't know this, but the best way to keep your tool up in 2024 is not by doing stretching exercises. You only need
The F-100 is one of our primary tactical support weapons systems. This aircraft has a proven history of outstanding performance. One of the reasons for this dependability is the rugged power plant. For one, a high-performance aircraft is adaptable to many missions. It is used for reconnaissance, as a tactical fighter, and as an interceptor. Approximately 30,000 pounds of thrust is developed by its twin engine. The F-102 is the first operational Air Force Delta Wing aircraft. The performance characteristics of this weapon system are ideally suited for intercept missions. A reliable power plant is essential for the success of any mission. The F-102, 101, and 100 are all powered by the rugged J-57 engine developed by Pratt & Whitney. The individual engines vary somewhat, but for the most part are the same fundamental design. The J-57 is a dual compressor engine. The engine consists of the following components: the inlet, the low-pressure compressor, the high-pressure compressor, the diffuser case, combustion chamber, the first, second, and third stage turbines, the afterburner, and the exhaust nozzle. The low-pressure compressor, referred to as N1, is driven by the second and third stage turbines. The high-pressure compressor, N2, is driven by the first stage turbine. These two units, or spools, are not mechanically connected. The J-57 operates on the same basic principle as all jet engines. Pressure presented in graph form below the basic engine outline, and velocity are increased by a series of rotors in the compressor section. A compressor bleed system prevents compressor instability when the engine is operating at reduced power. The compressed air passes through the diffuser into the combustion chamber, where the air expands, thus reducing somewhat the velocity and pressure. Fuel is mixed with a portion of the air to form the combustible mass. When combustion occurs, the gases are expelled through the turbine. At this point, power is extracted by the turbines to drive the compressor. The remaining energy, expelled through the exhaust nozzle, provides the thrust. Since exhaust nozzle and turbine discharge pressures are relative, turbine discharge pressure is used as a parameter to determine thrust. Thrust is the measure of force developed by the engine. Force is determined by mass times acceleration. Mass is the weight of air and fuel passing through the engine. Acceleration is the difference between inlet and the turbine discharge quantities of this mass. Thus, thrust may be expressed by the formula force equals mass times acceleration. The engine trim charts are based on this formula. Additional thrust is obtained in the afterburner by increasing mass and acceleration at that stage. The basic engine pressure ratio during afterburner operation is maintained by increasing the exhaust nozzle area. Efficient engine operation depends on correct fuel schedule. The basic components of the J57 main engine fuel system are fuel pump and fuel pump transfer valve, fuel control, and the pressurizing and dump valve. The fuel pump is a dual-element spur-gear pump. One element supplies fuel to the afterburner, the other to the main engine. The fuel control meters the fuel required to operate the engine through its full range. The pressurizing and dump valve supplies the main engine fuel manifold and drains the manifold at engine shutdown. At engine start, fuel enters the pump through the impeller where the pressure is increased. This provides a positive pressure head to the main stage. At this stage, the fuel reaches output pressure. The pressurized fuel closes the fuel regulating transfer valve and the afterburner check valve and flows into the fuel control. The main metering valve is closed at this time. A portion of this fuel passes through the minimum flow orifice through the signal line to the P&D valve. Since the control is in bypass, pressure does not build up enough to close this valve until the power lever moves from cutoff to idle. When the power lever is moved to the idle position, the fuel dump valve closes. The main metering valve opens. The cutoff valve moves off its seat. The pressure loading valve opens. The P&D valve inlet check valve opens. And the fuel is supplied to the primary side of the fuel manifold through the pressurizing and dump valve. At approximately 74% RPM, the fuel pressurizing valve will open to supply fuel to the secondary side of the fuel manifold. The J57 engine uses a primary and secondary system in order to obtain the highest possible fuel flow with the shortest possible flame. At low RPMs, only the primary side is used. When the emergency system is selected, the actuator positions the pilot valve to direct pressure to the shuttle valve system. The shuttle valve blocks off metered flow and provides a port for unmetered fuel to the emergency throttle valve. This mechanical valve controls the flow of fuel. The afterburner element of the fuel pump will supply fuel to the engine in the event of main element failure. The primary function is to furnish fuel for the afterburner.
I'm David Seaman. You're in safe hands for the Euros with Betway. Get up to £70 in free bet.
The other components of the J57 afterburner system are the afterburner fuel control, exhaust nozzle control, igniter valve, and the mechanical shutoff valve. The relative position of the components varies according to engine model. The afterburner fuel control meters fuel to the AB spray box. The exhaust nozzle control directs compressor discharge air to open and close the nozzles. The igniter valve injects fuel into the combustion chamber, creating a streak of flame to ignite the afterburner. In the event of electrical failure, the mechanical shutoff valve will terminate AB operation at approximately 80% RPM. Rotation of this valve causes AB stage fuel to bypass through the AB fuel control regulator valve. The fuel control unit is carefully calibrated on the test bench to assure accurate engine fuel schedule. The main functions of the fuel control are to maintain acceleration schedules below compressor stall zone, to prevent over temperature during acceleration, prevent lean die-out during deceleration, and to maintain any selected engine speed within operating limits regardless of altitude. The fuel control senses engine RPM, inlet temperature, and burner pressure to supply the correct amount of fuel for any ambient condition. When calibration has been completed, all external adjustments, except the idle and military trim screws, are sealed. These seals are installed to protect test bench precision calibrations and must not be removed. The J57 engine will provide relatively trouble-free operation when all systems are functioning correctly. However, the systems must be properly rigged and adjusted. One of the most critical engine adjustments is the rigging of the fuel control linkage. Full range movement is obtained only when the fuel control and afterburner mechanical shutoff valve levers are correctly positioned. The levers are set to predetermined angles. A protractor or etched template is used to set the linkage at these angles. The protractor is positioned at the oil pump and accessory housing plug to establish a reference angle. This reference angle will be used to adjust the fuel control lever. With the fuel control lever in cutoff position, the difference between the reference angle and this reading must be the number of degrees specified in the tech manual. It may be necessary to readjust the fuel control lever to obtain the correct angle. The fuel control lever and serrated spacer are ratcheted to give the desired angle. The fuel control position, which, when all other linkage is connected, will close the afterburner mechanical shutoff valve. The power actuating rod is then attached to the fuel control lever. Move the mechanical shutoff lever to the detent position. The rod, connecting the cross shaft lever and mechanical shutoff valve lever, may have to be adjusted to the specified length. The AB mechanical shutoff valve is held in detent position, which has already been adjusted to the specified length, will fit. Then all connections are tightened.